there's going to be something of a change of tack today. We're going to look at atmospheric chemistry and atmospheric processes more generally. One of the reasons for wanting to do this, there are two reasons. One of them is that as combustion scientists, we ought to be aware of the impact of combustion in the atmosphere. So what are, inevitably, certainly at present, combustion leads to emissions to the atmosphere. And we need to understand what those emissions are and what they do. Secondly, and this is not really a justification as far as you're concerned, but for me, this is an area that I'm interested in. It's a remarkably similar approach that's used in atmospheric processes to combustion. For me, as a chemist, I'm involved in measuring rate coefficients for reactions, in modeling reactions that are involved in the atmosphere. Our group also does measurements in the field, and that's very similar to making measurements in a flame or in a combustor generally. So what you're doing is trying to understand what's happening in the real system. And thirdly, there's modeling. So fluid dynamicists are prevalent in atmospheric science, and they need to mod. What is a big difference, though, is the feedback between the chemistry and the flow is pretty well non-existent in the atmosphere. So in combustion, that feedback, the heat release that comes from the chemistry, is important in driving the fluid dynamics. But that isn't the case in the atmosphere. So the linkage between the chemistry and the atmospheric transport is somewhat different than that in combustion. Okay, so what are we going to talk about? So we'll start off with just a very brief discussion on physical processes in the atmosphere. There won't be any any detailed discussion of this at all. Many of you know much more about this. The fluid dynamicists amongst you know much more about this than I do. But it will just be to set the scene and look at timescales of processes. Then we'll look excuse me, at emissions of organic compounds and nitrogen oxides to the atmosphere. And those are important in terms of chemistry and in terms of climate change. We'll look at the atmospheric chemistry of the oxidation of these organic compounds and the influence of NOx on that process. We'll look at air quality, ozone, and this is not ozone in the stratosphere, this is ozone down at the surface in what's called the troposphere, particulate matter, nitrogen dioxide, and look at and make distinctions between local, regional, and hemispheric scales as far as air quality is concerned. We'll look at climate change, say a little bit about radiative forcing, and about greenhouse gases, and about aerosols and clouds, which influence climate. And the albedo. The albedo is the ability of the Earth to reflect radiation. And that's obviously differs from a region which is covered with snow or a region which is covered with cloud from a region which is basically soil for agriculture. And then finally we'll finish up by asking the question, how well do we understand atmospheric chemistry? And this rather similar to what we were talking about yesterday, this is a comment on the need for this sort of integrated approach, this modeling, field measurement, laboratory measurements approach to things, and developing a fundamental understanding of the chemistry that lies behind the processes occurring in the atmosphere. And what one can find out is that our understanding is not as good as it should be, and not as good as it should be in quite fundamental ways and in practically important ways. And that's what we'll talk about at the end. Okay, so just let's have a look quickly at the structure of the atmosphere. So if you look at the pressure in the atmosphere, then it decreases as you go up in altitude. You know this because of the need to pressurize cabins in aircraft. The fact that if you go to the top of Everest, people need to carry oxygen with them. So the pressure is decreasing, and it's simply a barometric process in which the pressure goes down as the altitude goes up because of what you've got to do is balance the forces and bear in mind the importance of gravitation. And the pressure decreases roughly exponentially with altitude. Atmospheric scientists tend to make plots which are rational, but which are different from the way in which we normally do them. The independent variable is the altitude, and normally that would be in the x-axis, and the dependent variable is the pressure. But because it's physically appealing to plot altitude going up, this is the way that it's generally plotted. So this is the independent variable on what is ostensibly the y-axis. So that's the altitude going up, pressure roughly exponential, and there's something here called HS, which is a scale height, which depends upon the Boltzmann constant times temperature divided by the mass times the gravitational constant. You might think on the basis of that equation that there would be some sort of separation of species in the atmosphere because of their differences in mass. But that basically doesn't happen because the mixing is so strong. So if we're looking at the mass that we need to put in here, the molar mass that we put in is 28.8, which is the mean of the mass of nitrogen and oxygen, allowing for the differences in their atmospheric composition. And then this is the temperature. This is the temperature as a function of altitude. And it shows this interesting behavior. Initially, the temperature goes down as we go up in altitude. And again, you know this from looking at the window in an aircraft as you go up in altitude. And this is the main process of heating the atmosphere here is convective heating from the surface. And so that's going to be more effective close to the surface and gets less and less effective as you go up. There is also absorption of infrared and of some visible UV radiation in the atmosphere that also contributes to that temperature. And that's important because if there were no carbon dioxide in the atmosphere, what carbon dioxide does, as we'll see, is it absorbs infrared radiation, and it especially absorbs infrared radiation near the top of the troposphere because there the temperature is low and the difference in temperature between the surface, which is emitting the radiation, and the absorbing CO2 is most effective near the this is called the tropopause because the temperature of the CO2 is lowest there. So if there were no CO2 absorbing that infrared radiation emitted from the surface of the Earth, all of that infrared radiation will be lost to outer space, and the net result would be that the temperature of the surface would be about 250 degrees. So it would be a lot colder. And basically life would not be sustainable, certainly in its present form. So the CO2 is very important. It was recognized initially by a man called Arrhenius, who also gave rise to the Arrhenius expression for rate coefficients, and the importance of what's called the greenhouse effect, holding in some of the energy in the atmosphere and the Earth's surface because of this absorption by CO2. Let's have a look at atmospheric transport. First of all, random motion. Molecular diffusion is very, very slow. That's diffusion coefficient under the pressure conditions that apply, and it's remember that the average distance traveled in one dimension in time t, if you've got purely diffusive processes, is the square root of 2 times d times t. And so this molecular diffusion coefficient is very small. And so the main mechanism for diffusion in the atmosphere is what's called eddy diffusion, where small packages of air move together. And the diffusion coefficient there is much, much larger, and so the distances traveled in a given time are correspondingly larger. Molecular diffusion is more important at very high altitudes where the pressure is low. Oh, sorry, I should have said that the temperature in the stratosphere increases with altitude, and the main mechanism there is heating by exothermic photochemical reactions. And there is a consequence of this, these profiles, because you've got colder, denser air at higher altitudes in the troposphere, then there is good mixing in the troposphere. So you can look on the troposphere as being a relatively well-mixed chemical reactor, if you're a chemist. The stratosphere, on the other hand, isn't like that, and you get layering and significantly less good mixing. So that's diffusion. And then we have, there is another point which we need to make, that although it takes a month for vertical mixing using these sorts of these diffusive processes, there are weather patterns that lead to uplift of air. And this uplift can occur really very rapidly. We'll look at one particular important process, which occurs mainly near the equator, but many weather patterns lead to uplift of air, not by a diffusive process, but by a forced process resulting from the weather. Then directed motion, and this is really, that's one aspect of that. Advection corresponds to winds. So if you look at a plume from a power station, then you can see both the horizontal and the vertical motion of the air just by looking at that plume from a power station. And this occurs on a variety of scales, local scales. So you get local winds, for example, offshore winds at the coast, offshore and onshore winds at the coast, depending upon the time of day. Regional processes, which are weather events, and global processes, the Hadley circulation, which I'll show you in a minute. One of the interests, if you talk to meteorologists, then they're very, very keen to point out that there are differences between weather and climate. So weather is really local or regional processes, and climate is what's going on in the globe as a whole. There is much, much more variability in the weather than in the climate. So the climate is evolving slowly. Weather patterns can change really very quickly. So this shows winds due to weather patterns, and so you have high pressure regions, low pressure regions, and the wind moves from the high pressure to the low pressure regions. But we've got to remember also that the Earth is rotating, and so there is a Coriolis effect where the wind doesn't cross these isobars perpendicularly. It's affected by the Earth's rotation, and so it crosses at an angle. And the direction of approach is different in the northern and the southern hemispheres because of this rotation process. Global circulations, to a first approximation, we can look on the Earth in this following way, that it's hot at the equator, cold near the poles. And so what happens is that as you go up in altitude, then the pressure goes down, and there is this upward transport which results from that lower pressure. The scale height, if you remember, depends upon temperature, and so there is a difference in a cold region from a warm region, and so we can get uplift here, transport, and then down this downward transport over the cold region. And so if no other things were going on, if it was simply hot and cold, this is what transport would look like, global transport would look like, going from the equator out to the poles at high altitudes and a return coming back at low altitudes from the cold regions to the hot regions. And there would then be this partition between these, what are called Hadley cells, with a barrier to circulation occurring at this, what's called this intertropical convergence zone. So there's rapid vertical mixing near the equator, but very slow transport from the northern hemisphere to the southern hemisphere. It's a little bit more complicated than that because of vegetation effects, differences in the way that differences in the humidity of the air, which affects, I haven't gone into it, but it affects that scale height equation if the air is humid. So differences in humidity with latitude, differences in vegetation, generate what are called cells. So these are the Hadley cells, which are close to the equator, and so the warm, moist air rises and then circulates within this Hadley cell and descends at higher latitudes. And similarly in the southern hemisphere. These are called Hadley cells. And then we have what are called feral cells, in which the circulation goes in the opposite direction because of the regional conditions over this area. And then finally these polar cells where the circulation is very similar to that in the Hadley cells. So that's transport going with latitude or across latitude. There's also transport from east to west and west to east, crossing lines of longitude. And these transport processes are much less efficient and effective down near the equator, and you have regions where the transport is really very slow down here, called the doldrums. But then this rapid transport, which affects very strongly the way in which the times taken for traveling by air in easterly and westerly directions. And up here, there's something called the jet stream, which is really a very, very effective mechanism of transport that takes air in these directions here. And there are lots and lots of other influences which are giving some cause for concern. There's ocean transport, and there's strong current which takes air in this direction down here. And as far as Western Europe is concerned, so this is what's called the Gulf Stream. As far as Western Europe is concerned, that's what keeps it warm. And so if you look at Western Europe compared with Western US, then the temperatures at the same latitude in Western Europe, are very much higher in winter than those in Western US. But there is concern about just how stable that Gulf Stream is and the effects that it will have on weather. There's also been a lot of interest recently in the jet stream moving up and down with latitude. And suggestions that this may be related to melting of the polar ice cap, the Arctic ice cap. And this certainly is thought to be one of the reasons. Any of you who come from Europe or have spent time in Europe this year will know that the weather has been absolutely appalling, with lots and lots and lots and lots of rain, especially in the UK. And one of the suggestions is that this jet stream moving up and down is one of the reasons for that. A lot of flooding recently in Central Europe also. One of the things that happened last week was that the Met Office, the Meteorological Office in the UK, had a special meeting to debate what is going on with the weather. The news media made great score by this. Nobody believes anything that comes out of Met Offices because they occasionally get things wrong about the weather, and so they're held up as a laughingstock, despite the fact that it is a very, very impressive organization. But they were laughed at because of they were having this meeting to worry about what was happening to the weather. But when I get back, there is a meeting in Leeds which will discuss what the findings were of this group meeting at the Met Office. So it's going to be interesting to see what are thought to be the reasons why our weather has changed quite significantly over the last few years. So important to recognize the difference between weather and climate. Let's have a look at horizontal transport and the timescales. Going around, especially at temperate latitudes, takes about 2 weeks going around the world. It's slower going north and south, 1 to 2 months. And it takes about a year for air to move from the northern hemisphere down to the southern hemisphere. So these are horizontal processes. But they're important if you're thinking about the timescales for chemical transformations. Okay, let's turn to emissions. And so this is the global budget for methane. And the units are teragrams of methane per year. And the total emission is around about 535 teragrams. And natural sources about 160 teragrams, anthropogenic human sources something like 375. Wetlands, termites, oceans are the natural sources of methane, and anthropogenic sources are natural gas, coal mines, enteric fermentation. This is cows mainly, who have a big effect on methane in the atmosphere, rice paddies, and so on. Cows may seem to be a fairly natural entity, but they're farmed, and so that's why they're included in anthropogenic sources. The sinks of methane, the major sink is reaction with the hydroxyl radical. So chemistry is vitally important in removing methane from the atmosphere. And then some transfer to the stratosphere and some uptake by soils. These are very carefully constructed calculations, but the uncertainties in them are massive. So the actual values of both the sources and the sinks, we'll have a look at what's happening to methane globally in a minute, but these are pretty close. They should be almost the same, but as we'll see, methane is increasing slowly throughout the globe. So here's the historical methane trend. So many of these are determined from, you see here, Eurocore. They're basically determined from ice core samples, especially in the Antarctic. So they take an ice core, they analyze, and what's happened is that air has been trapped in small bubbles in the ice and frozen in the ice, and it doesn't escape. And then by taking an ice core, you can analyze the composition of these bubbles and determine what the composition of the atmosphere was. And so you can see that it stayed fairly stable up until about 1800, the late 1700s. So this was the Industrial Revolution, and then methane has continued to increase since then. This is a recent methane trend going up to 2000. Notice that it varies slightly throughout the year, and we'll talk about that in a minute. And I downloaded this morning so that I could have the latest plot. So this is going up to the middle of, or the early 2013. And you can see that there was this strange arrest in methane in the 2000s. And there are many suggestions as to what the source of that arrest in the rising methane was. We really don't understand, because we don't understand the sources and the sinks at the level of detail we need in order to interpret this. But it started rising again now. Okay, so that's methane. We'll come back to it in a moment. But here's the global budget for CO. Sources, fossil fuel combustion. So these are teragrams of CO a year. Biomass burning, vegetation, oceans, oxidation of methane, oxidation of other hydrocarbons. Biomass burning here doesn't refer to controlled combustion in a combustor. It refers to forests burning, especially in boreal regions in Canada and Russia. And then the sinks, again, tropospheric oxidation by OH, transfer to the stratosphere, and again, uptake by soil. Once again, tropospheric oxidation by OH is very much the most important thing. And CO reacts with OH significantly more rapidly than OH, and so its atmospheric lifetime is considerably shorter. Emissions of what are called non-methane volatile organic compounds, or VOCs. And so these are things like ethane, ethene, benzene, toluene. And so these are the sources of them. And the anthropogenic VOCs are of the order of 142 teragrams a year. And there's the distribution. So fuel production, fuel consumption, road transport, etc. And then biogenic. So this is about 142 teragrams a year. Biogenic emissions are of the order of 1150 teragrams per year. Many, many more emissions coming from biogenic sources. So these are basically plants emitting, and especially trees. And the most important, and we'll come back to this later on, the most important VOC, biogenic VOC, is isoprene, which is a C5 hydrocarbon. Yeah, so it's a diene. So it's basically butadiene with a methyl radical on it, with a methyl group on it. And these emissions are massive. They're almost as large as the emissions of, they're very comparable with the emissions of methane. So methane emissions and isoprene emissions are both very, very significant. And some years ago, Ronald Reagan made a comment which was somewhat ridiculed about trees being important sources of pollution, but there was a very significant element of truth in what he said, because isoprene contributes significantly to ozone formation in the troposphere. Okay, let's look at removal of organic compounds from the atmosphere by reaction with OH. And this is one of the most important ways in which they're removed, as we'll see. So we can talk about, if you remember, we said that if a process is, we can have a pseudo first-order reaction, then the lifetime of the species undergoing that reaction, the minority species, is given by 1 over k times the concentration. So if you go back to the very first lecture, the lifetime is equal to 1 over k times x. And so if we... now, this is a slightly different situation. The concentrations of the hydrocarbons are very much higher than those of OH. But the OH is regenerated in the atmosphere, and its concentration is typically 1 times 10 to the 6 molecules per centimeter cubed. So that's something like, what? It's about it's less than 1/10 of a part per trillion in the atmosphere. So it's very, very low concentration. but it's sustained. And that's a sort of average concentration night and day. And so what we can do then is we can say that as far as these hydrocarbons are concerned, they're primarily removed by reaction with OH. And so the lifetime is going to be 1 over the rate constant for the reaction times the concentration of OH. So what does this mean? Well, the rate coefficients in units of 10 to the minus 12 centimeters cubed per molecule per second. For methane, 7 times 10 to the minus 3, CO 0.24, isoprene 110, ethane 0.25. Isoprene reacts incredibly quickly with OH on almost every collision. Yeah.
How does the distribution of OH in the by altitude compare to like air?
It varies. A more important variation is actually its variation with latitude and longitude, and its highest concentrations are in the tropics. So that the highest OH concentrations are in the tropics. The variation with altitude is driven by the concentrations of ozone, as we'll see, and so it increases slightly as you go up in altitude. So it's driven by that and also the concentrations of other things that are around. Okay, so using this concentration and these rate constants, we can determine approximate lifetimes. Methane is about 5 years. CO is about 7 weeks. Isoprene is only about 3 hours. Ethane is about 7 weeks. And so that determines the atmospheric distribution. What we said was that the timescale for transport from the northern hemisphere to the southern hemisphere is of the order of a year. But this means then that methane is reasonably, I'll qualify that in a minute, reasonably homogeneously distributed throughout the globe. The CO concentrate, the main emission sources for CO are in the northern hemisphere, and so the CO concentration is much higher, significantly higher in the northern hemisphere than in the southern hemisphere. So we've made measurements in clean regions in Western Ireland and also in Tasmania. And the ratio of methane to CO, which is what determines what happens to OH in these clean regions, is very different in Tasmania and in Western Ireland. So CH4 is distributed globally with only a slight northern hemisphere, southern hemisphere difference. Isoprene is found only close to its very extensive sources. So the isoprene concentration falls very quickly as you go away from the sources. The oxidizing capacity of the atmosphere is often discussed, and this is a very important quantity because, for example, it's the way in which methane especially is removed from the atmosphere. And it depends mainly on the concentration of the hydroxyl radical. And so it's important that that concentration is maintained. And it is. It's a pretty stable quantity. So this is from the previous methane plots I showed you were from a NOAA website. So if you want to get information on these global distributions, global concentrations, then there's a NOAA website which you can find them. Just Google global distribution of methane or something like that. And this is taken from that slide. I'm afraid it finishes in 2000. I should have downloaded a more recent one. But so this is time, this is year going along here. This is latitude. So there's the equator, or the equator is somewhere in here. And there's the distribution going from about 1,800 nanomoles per mole. So that's basically parts per billion. Down to about 1,600. So the concentrations are slightly different, but relatively close. If you look at the annual variation, then the concentration is highest in the winter. And that's because the OH concentration is highest in the summer. And OH removes the methane, and so its concentration is lower when the OH concentration is highest. So this annual variation arises because of the variations in the concentration of OH throughout the year. OH is formed mainly by a photochemical process, and so that's why its concentration is higher in the summer than the winter. And notice that when you go to the southern hemisphere, these things reverse. So we got the maximum here when there was the minimum in the northern hemisphere, and of course that's because the summer, when it's winter in the north, it's summer in the south. So let's have a look at the chemistry. And there are many similarities between the processes occurring in the atmosphere. They're a lot slower than in combustion systems, but there are many similarities. Okay, so the hydroxyl radical, it's the main tropospheric oxidant. What are its main global sources and sinks? Well, the primary source is ozone, photolysis. And ozone, below about 320 nanometers, ozone can be photolyzed to form this excited electronic state. So it's a singlet electronic state. The spins are paired. And it's a very reactive species. It can be deactivated by collision with a third body M, which in this case, again, is mainly nitrogen and oxygen. So O-singlet D collides with nitrogen and oxygen and gets deactivated to ground state oxygen atom. But the other thing that it can do is it can react with water. It reacts very quickly with water. O-triplet P, the ground state, doesn't react with water, but O-singlet D reacts with water to form OH. And we need to bear this in mind. We'll come across this once or twice during these lectures. The photolysis leads to O-singlet D, and then there's a branching between the activation, which regenerates ozone because this oxygen atom reacts with an O2 molecule to regenerate ozone. So there's deactivation that regenerates ozone, then this reactive process that forms OH. And so what this does is it shows the actinic flux coming down here. So that's the light coming from the sun, which falls off dramatically as we go down below 300 nanometers. And that's because of the presence of ozone in the stratosphere. So ozone in the stratosphere acts as a filter and stops this UV radiation coming down to us. And so that's why there was all the concern about concentrations of ozone in the stratosphere because of the influence of things like CFCs. And then this is the cross-section for ozone. And we take to form O-singlet D. And then this is the product of these two. So there's this very big peak in the production of O-singlet D around about 300, 320 nanometers. And that's where the ozone is photolysed to form O-singlet D, and that's the photochemical region where ozone is photolysed to form OH. The sink is mainly oxidation of reduced species. So OH reacts with CO and methane, and those are the main ways in which OH is removed in the atmosphere because of the preponderance of these things. It also reacts with isoprene, and in regions where isoprene is very high, then this is a major sink for OH in principle, but we'll come back to that later on. Okay, let's have a look at methane oxidation. Initiation by OH formation from ozone photolysis. I should say also there are other sources of OH. So, for example, HONO is formed in the atmosphere by chemical processes, and that forms OH plus NO. The only problem with that is that the HONO itself is formed from OH, and so that in the end is a null source. but also formaldehyde is photolysed in the atmosphere, and one of the things that it does is it forms HCO plus H, and then these react with O2 to form HO2 plus CO, and again with O2 to form HO2. And HO2, as we'll see, can lead to OH formation. So there are other sources, but the photolysis of ozone is the major one. Right. So OH reacts with methane to form a methyl radical, just the same sort of process we get in combustion, but there's a lot of O2 around, and so the first thing that happens to this methyl radical is that it forms a peroxy radical. In combustion systems, the temperature is higher, and the methyl radical reacts with other species as well. But in the atmosphere, it's converted invariably to methyl peroxy. And we can see that occurs very quickly because the rate coefficient for CH3 plus O2 is about 10 to the minus 12. The concentration of O2, so O2 is of the order of 10 to the 18 molecules per centimeter cubed, depending upon the altitude. And so taking this rate coefficient and that concentration gives you a lifetime for the methyl radical in the atmosphere of about a microsecond. So it's very, very quickly converted to methyl O2. So methyl O2 then reacts with NO to form a methoxy radical plus NO2. Methoxy reacts with O2 to form HO2 plus formaldehyde, and HO2 reacts with NO to regenerate OH. So this is the way in which OH is formed from the HO2 radical. So you can see this interaction between the organic compounds and nitrogen oxides, NO. So the sequence of reactions is initiated, or this cycle is initiated by OH, and OH is regenerated at the end. So it's a chain reaction. It's a very short chain reaction. And what one does is one converts NO into NO2 and forms these oxygenated species like formaldehyde. Secondary radical formation can occur. HCO reacts with OH to form, and O2 to form HO2 plus CO plus water. So basically this reaction is producing the formal radical HCO, which react rapidly with O2 to form HO2 plus CO. Formaldehyde can be photolysed. There are two processes. One of them gives H2 plus CO, so molecular products, and the other one is the one that I discussed over there, which forms HCO plus H, which in the presence of O2 gives you HO2 again. So this is secondary radical formation in this methane chain. And then the termination reactions, we can get reaction of OH with NO2 to form nitric acid. And in the atmosphere, nitric acid is generally deposited to the surface. It can be photolysed, but much of it gets simply deposited to the surface often in rain. But it can be both what's called dry deposited and wet deposited. So that's a reaction between OH and NO2, and then we get these peroxy radical reactions, HO2 plus HO2 forming hydrogen peroxide, and CH3O2 plus HO2 forming methyl hydroperoxide. As we'll see, these terminations, quite logically, if you look at those termination reactions, these terminations depend upon the amount of NOx that's around. If there's a reasonable amount of NOx, if it's a reasonably polluted area, then this is the main termination reaction, and these are important when the atmosphere is very clean, in clean areas. And as we'll see, that those extremes of termination, often the two are both occurring, but those extremes of termination affect the way in which we develop policy to improve air quality. Okay, a general oxidation scheme for VOCs really follow that for methane. Ozone plus H nu gives O singlet D plus O2. O singlet D plus water gives OH. OH plus RH forms RO2. And that reaction is going to depend upon the nature of RH. If it's an alkane, then it's a simple abstraction process, as with methane. But if it's ethene, then the OH adds to the ethene to form a hydroxy alkyl radical. And then RO2 reacts with NO to form NO2 plus RO. RO reacts and eventually forms HO2 and some sort of oxygenated species. And then HO2 plus NO reacts to regenerate OH. Key reaction from all of this, notice that in all of these reaction schemes, we're converting NO into NO2. And what happens to the NO2 is that it's photolysed to form NO plus O. That's ground state oxygen. And the ground state oxygen reacts with O2 and a third body to form ozone. And that's the only way in which ozone is formed in the troposphere, from the photolysis of NO2 and from the reaction of the oxygen atom that you produce from that with O2. So overall, what we've got here is that NOx plus VOCs plus sunlight, the sunlight is important in generating the OH initially, lead to the formation of ozone, and as we'll see, they can also lead to the formation of secondary organic aerosol. So there's the ozone, and that's one of the key pollutants in determining regional air quality. So this is looking at that same chemistry, but now as a cycle. So the VOC reacts with OH, forming RO2. RO2 reacts with NO, converting the NO to NO2 and generating RO. RO reacts, forms HO2 and some carbonyl, and then HO2 reacts with NO, converting it into NO2 and regenerating OH. Then, so those NO2s can be photolysed to form ozone. And it's basically a chain reaction. And the length of the chain depends upon the degree of pollution. So in a fairly polluted region, then the chain length can be quite long, of the order of 5 or 6. Do you know what I mean by chain length? Is everybody happy with the concept of a chain length? Well, okay, some faces don't look very happy. So let me explain. Basically, you're starting off this chain reaction by a reaction between OH and the VOC, and you're going round the chain and regenerating the OH. And what happens is that, in addition, you're getting termination processes. So the OH is reacting with NO2, and the HO2 and RO2 are reacting with other proxy radicals. So terminations occur. And the chain length is basically the ratio of the rate of propagation round this cycle to the rate of termination. And typically, it can be something like 5 or 6 in a polluted region, more generally something like 2 or 3. In the experiments that we did in Tasmania, where the air is very, very clean, the chain length was something like 0.2. So in other words, the termination steps were 5 times as fast as the propagation steps. So these are some additional pieces of information that we've already... So this is basically summarizing what we've had in the last few slides. And these carbonyl products are quite important in terms of the subsequent chemistry, both in terms of generating radicals like formaldehyde there, but also, as we'll see, in forming secondary organic aerosols. Other oxidizing species, NO3 is formed by the reaction between NO2 and ozone, giving NO3 plus O2. And it's removed by, this is not very clear, this should be NO2 plus NO3 plus M, giving N2O5 plus M. So there are a wide range of nitrogen oxide species in the atmosphere, and NO3 is one of them. And it's a radical, it's photolyzed and rapidly lost during the day, so it's not an important species in the day. Clearly, OH is an important species in the day, and its concentration is generally very low at night. And it's important in the day because it's produced by photolysis. It adds to alkenes to form nitroalkyl radicals, which form peroxy radicals in the usual way. And so it leads to very similar chemistry, but with nitroalkyl radicals present rather than non-nitrogenated radicals. Ozone reacts with alkenes. The reactions are quite slow for most species, but the concentration of ozone is relatively high. So these are important reactions both day and night, and they form what are called these Kriegi biradicals. I'm sure you don't remember, but if you look back to the slides on the first day, I mentioned some experiments done at the Advanced Light Source in Berkeley by the Sandia group, in which they made the first detection of these Kriegi biradicals using pulse photolysis. So these Kriegi biradicals are important, and so this is an important oxidation mechanism. And one of the things that can happen is ozone plus alkene can form OH. And this is a way in which OH can be formed at night. So ozone plus alkenes occurs at night, and so there is a route to forming OH at night. And we detected OH at night at low concentrations, but nevertheless detected it in experiments in Western Ireland. And then photolysis. So photolysis is an important way in which VOCs are, the oxidation of VOCs starts in the atmosphere. And something like methane isn't photolized in the atmosphere, but species with C double bond O groups in them, aldehydes, ketones, etc., are photolized in the atmosphere. Why should we worry about ground level ozone? The main reason is because of health impacts. So its irritant properties, it produces an inflammatory response in the lung, and this is especially problematic for people with asthma. And often, when ozone is high, then people with asthmatic problems are often advised to stay in. Should say that because of policies throughout the world, the ozone concentration, as we'll see, is significantly lower than it used to be. Ron will tell you that in Los Angeles, in the 50s, 60s, the ozone concentration could be really very, very high indeed. But controls have reduced it considerably. But those controls have been imposed because of these problems. It's not clear whether there's a threshold for health effects. It may be that even tiny, tiny concentrations of ozone have an impact. The WHO is the World Health Organization, and it has a guideline of 50 parts per billion as the maximum concentration that ozone should reach, measured as a running 8-hour mean. So the European Union has a somewhat higher requirement of 60 parts per billion, so it's a bit more relaxed than WHO. In the UK, we have a 50 parts per billion requirement. And then in the US, it's got what's called an objective value, which is somewhat higher still, of about 75 ppb. Concentrations are highest during what are called summer episodes, when the air is very still and when there's a lot of sunlight around. But because of controls, regional controls on VOCs and NOx, those summer episodes are getting less and less extreme. And what we're more and more worried about, is the sort of general level, which is creeping up and up and up because of, as we'll see, because of hemispheric processes. Ozone also has an adverse effect on crop yields, on tree growth, and on the composition of natural plant communities and on materials. You know that rubber is affected by exposure to ozone. The ozone adds across the double bonds in the rubber and degrades the rubber. So materials are also affected. So there are very good reasons for trying to control the concentrations of ozone. Okay, we'll break there, and then we'll be back to talk about NOx budgets at 10 o'clock.